So we want to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified axis. So the curves we have are y equals x to the 6, so I have that over here in red, and y equals 1, that's the blue one, and I want to rotate the region they bound about y equals 4. So let's be clear about that region we're bounding here. There we go. So that would be this region right here. And now I have that screenshot. It's a good idea that you are in the practice of writing these kinds of things on paper. So I'm going to also make the sketch over here. So here's my X and Y axis. Let's say this right here is 1, and about there would be -1, and I need to go up 1, 2, 3, up to 4 here. And my axis of rotation, to that green like the other picture, comes through there roughly. I have my blue line through y equals 1 out here. And then we'll draw the red curve. And really all I care is where it intersects here. So then it scoops low at the bottom and then comes up. So something like that. And again, it's this region here that we're going to rotate. Can't emphasize enough how important it is to draw these. That's my axis of rotation there. And what's that going to look like? That's going to help us figure this out. So I'm going to rotate about that. We're using slices, and my slices are going to be perpendicular. So a slice here is going to be just this little strip, this little tiny strip there, and that's going to get rotated. Now, a couple things to consider. When I rotate that slice right there, what I'm going to end up with is this circular washer. As that rotates through, right, this axis right here, and it's going to have some thickness to it. So maybe something like this is my washer that I'm creating. And I'm going to stack a whole bunch of those washers to make a 3D shape as I spin this thing here. So what's that going to look like? Well, the inside of it is this line, this blue line, spinning about the axis of the green line. So that's going to just give me a cylinder. So let's just draw a cylinder. So that's going to be the inside of this shape. And the outside of the shape is this curve, like kind of padding around the outside. So that's going to be something like this around the outside. And so I'm just going to redraw this a little bit, make this a dotted line because we're not going to see that. And it's the red curve on the outside that's going to generate the outside of this 3D object. And this green line I'm making dotted is the inside of the cylinder. So it's like a toilet paper roll, but it's compacted on the ends, rounded on the ends, and puffy in the middle. So you can kind of imagine that shape right there is what we're creating by a bunch of stacked washers when we make that. So what I need to do is, this is my cross-sectional area that I need to find here. Oops. Choose this for the area. So I need to find the area of this washer cross-section, and the thickness of it to get volume, that's going to be my dx, the way I set this up. So my thickness of the washer is my dx. So how do you find the area of a washer? Well, a washer is just a circle, and that circle has an area, so we're going to use the area of a circle. Now that's a disk when I look inside, and what I want to do is I want to cut the center of this disk out to get the washer. So in order to do that, I've got a big circle basically minus a little circle in the middle, and that big circle is going to have a radius. So we'll say that's big R. Let's use a different color for that. And big R is going to be the distance from the center to the edge there. And then I'm also going to have this little r circle here. And that's the distance from the center to that edge. And then the area is the area of the big R circle, so that's pi big R squared minus pi little r squared will be the washer surface, and then to give that volume, we multiply by its thickness, in this case, the dx. So what is big R and what is little r? Well, let's look at the picture. We're rotating about this axis, so big R is the distance from here all the way to the red curve. Well, the distance from here to here, I would say, that's my big R. That would be 4 minus x to the 6th power. Right? Distance from here to here. And then my little r inside would be the distance from here to here. And that's just 4 minus 1, or 3. So again, this chunk, this washer that I'm going to build this with, a whole bunch of stacked washers, they just get stacked up, coming around. It's going to be pi big R is really 4 minus x to the 6th, and we have to square it, minus the little circle, pi minus little r, which is just 3 squared. And that's one washer's surface. Dx gives me the thickness of the washer. And if we add all those up, which is what an integral does, as x goes from 0, actually -1, excuse me, to 1, that should generate the volume of this shape, which is this padding all the way around this cylinder. Now we can clean this up a little bit. So a couple of observations I can make is the pi can be pulled out. Given the symmetry of this situation on each side of the y-axis here, I can double the integral from 0 to 1. So I'm going to go 2 pi and integrate as x goes from 0 to 1. Now, the 4 minus x to the 6th squared, if you think about a u substitution on that, if u was equal to 4 minus x to the 6th, our du would be -6 x to the 5th dx, and there's no x to the 5th hanging around outside. So u substitution is not going to work. You're going to have to carry up a square by multiplying 4 minus x to the 6th times 4 minus x to the 6th. And then we can subtract from that 3 squared, or 9. So let's do that next. So I'm just going to write that down here. That's going to give me a 4 times 4, which is a 16, minus the 9. Let's see, 16 minus 9 on a good day is 7. So I'm going to have a 7. And then we're going to have a 4 times -x to the 6th, and a -x to the 6th times 4. It's going to give me -8 x to the 6th. Negative times the negative is a positive. X to the 6th times x to the 6th is x to the 12th. 12th, there we go. So that is this product minus 9. So that's my new integrand. 7 minus 8 x to the 6th plus x to the 12th dx. So the hard part in these is setting up to figure out what your integrand is. Always worth trying to clean up your integrand before you find an antiderivative. So antiderivative here, we got our 2 pi hanging out front. Antiderivative for 7 would be 7x. Antiderivative for the x to the 6th, the 8 holds out, and we'll have x to the 7 over 7, plus antiderivative for x to the 12th would be x to the 13 over 13. And we're going to integrate that from 0 to 1. Cleaning that up a little bit more, we plug in the 1. So I'm going to have a 2 pi times 7 times 1 minus 8 times 1 to the 7th, which is 8. And then we have the over 7. And 1 to the 13th happens to be 1, so plus 1/13. And then minus, always double check the minus part. When we plug in 0, we get 0, 0, 0, which doesn't contribute anything. So then my answer here is that part right there. So next I'm going to clean up that And this problem probably wants an exact answer with pi. And rather than by hand finding a common denominator, I'm just going to use a calculator. All right, so there's my calculator. I'm playing with Desmos here. So I want to clean up my answer. So let's just do the 2 pi, and then I'm just going to play with this. So I had, let's see, it was, oops. All right, got it. 7 minus 8/7 plus 1/13. So I'm getting an answer of 32.28. Now I'm going to double check that in a couple of ways. I want to clean this up a little bit. And my common denominator is 7 times 13. So I'm going to plop the pi out of that for a minute. Actually, I can just come over here and do that. So I'm going to keep the 2. And then for a common denominator, I'm going to have to multiply that first 7 by a 7 and a 13. And this 7 needs a 13 in the bottom, so that's going to be a minus 8 times 7. Oops, I missed something there. 7 times. So that's the first numerator. There's the second numerator. And then the third numerator should be that 13 needs a 7 in the bottom. So plus 7. Let's see, did I get that right? 7 times 7 times 13. Get a common denominator for that one. 8 needs a common denominator of 13. Oops, there we go. And 13 needs a common denominator with a 7. That looks better. So that's telling me my numerator is 1080. So I think another way to write the answer then would be 1080 pi divided by 7 times 13. I think on a good day is 91. Got the same answer. All right. So I just wanted the fraction form on that. Instead of finding a common denominator for fun, if you have an arithmetic statement, most calculators will find a common denominator for you. All right. Playing with fractions is always good practice. The next thing I'm going to do is to double check that I did that correctly is use numerical integration to check it. But this is important. Your calculus teacher is probably going to want to see from you some sketches to get your setup here. Cleaning that up, they're going to want to see an integrand and an antiderivative, and then the beginning of an evaluation of that definite integral. And so we're going to confirm that we have the right answer. So far I have one possible answer, 37.28, which is also 1080 pi over 91. And I would go back to the original integral to check. I'm going to go from -1 to 1, parentheses, and I'm going to type it as I had it, pi times parentheses. That was 4 minus x raised to the 6th. That difference is squared. And then from that, I'm subtracting pi times 3 squared. And I want to close my integrand and indicate the variable of integration. And my answer matches. So provided my setup is correct about the integrand here, my setup was determined by my sketches. In this case, determining the outer function that's being rotated, the inner function that's rotated, so I subtract in the right way, and that my slices are disks, a disk within a disk, leaving a washer. So that's the washer setup for a rotational solid like this. Draw pictures to make sure you set up properly is the key, and double check.